Hi guys, and welcome to the fifth Genome2D Devcast. And as I promised last week, today we are going to talk about UI and the second part. There will be probably more parts because the UI part of the Genome2D is still being developed and there is a lot of things to cover. And I will also talk further on the 1.1 refactoring, which is ongoing as well. And today I will show you one of the major API breaking changes that will come to the 1.1 version of Genome2D. So without further ado, let's talk about the UI. I'm creating a simple editor for the UI because I think UI is one of the, if not the main part, which is edited using some kind of tool or some kind of text editor via syntax. I will show you both which you can do in Genome2D. So I decided to create a simple editor. It's not public yet. It will be public later. Maybe I will make it a donation stuff. I don't know. There is a lot of work on it, and I'm not sure I will have time with Genome2D and my main projects, which are built on top of Genome2D. So we'll see. But I decided to show it to you and use it inside this devcast because we can showcase the UI stuff a little bit better with it. So let's start. I'm going to compile the editor. I hope it will not crash, and it will. It's because it's still in development, and as well the UI is still in development, so there are a lot of stuff, especially inside the editor. The UI is pretty stable. I'm using it in my main projects as well, but the editor, there is a lot of stuff going on. Even though it looks simple, there is a lot of stuff going on. Like if you edit this, there is a ton of stuff that can need to be invalidated somewhere else. So this is the main window, is the scene editor. As you can see on the left, there is the UI hierarchy. This is the first child of the root. You don't see the root element of the, as we told earlier, there is a GUI component for Genome2D, which is on a node, and this GUI component has a root, which is always there. It's the root GUI element to tell, and this is the first child of the root. Because I don't want to show root here because you can't modify root, you can't delete it and stuff like that. So this shows you all the elements that actually you created. So the root is somewhere here if we imagine it. So I created a simple scene. We have one container and 4 children. Some people asked me if the UI supports hierarchy, because as I showed you, there is this relative and absolute positioning of stuff going on, and some of you asked me if we can have a container with the relative positioning and some kind of children inside the container that will also move. So we don't need to set the relative positioning on all the children elements and they will move with the container. Yeah, that's what's going on here. The elements are pretty much the same as nodes when it comes to hierarchy or native display list. They can have children, and can have other children, and they will invalidate their transform hierarchically. So if the parent moves, the children move as well, and I will show it to you. One thing I'm not sure I mentioned earlier is that compared to nodes, the UI elements don't support rotation. There is no rotation going on because rotation messes things a lot, and I'm thinking about adding rotation in the final state, something similar to CSS, because even if CSS, if you have some kind of layout and you position stuff there, the elements, you can rotate it, but it will not affect the layout. So for example, if we had some kind of grid, or let's say a horizontal list, so you had this element, this rectangle here. The next rectangle would be here, right next to the first rectangle, and if we rotated the rectangle, it would not affect the position of the second rectangle. So the rotation of the element doesn't change the actual layout computations of the and even the mouse computations of the element. So it's just a visual thing. It doesn't affect mouse. It doesn't affect the layout style cascading, or how to say it. It doesn't support the rotation yet. Even this post calculation rotation, as I described here. But I can add the final rotation because it can be useful for some kind of effects, for like you hover over a button and the label will rotate, or scale or something like that. So I will add these modifications that would be done only on the rendering. So all the calculations and stuff like that would be done without rotation. So if we rotate a rectangle here, it will not increase its actual bounding box, and it will not affect the other elements inside the parent, because it's useless, and it takes a lot of time to calculate, and I don't really see a use case for it. It's doable. It's just goniometric stuff, but and it is pretty easy actually. But why do it if it slows things down and it's not needed, except the rendering stuff I just propositioned. So let's add some kind of skin. So I have these skins here. What this editor does, I can show you here. Maybe go to asset editor. It enumerates all the files inside some kind of specified directory. You will be able to specify it now. It's some kind of root dot assets or stuff like that. So application directory assets. And as you can see, we have all these assets here. Oh, now it crashed. Anyway, so I will compile. It crashed because the font file isn't actually something you can render. At least the font file, the PNG that comes with the font file, is renderable, but this file is not renderable, and I didn't check it yet, so that's why it crashed. So let's stay with here. Now these are all of the assets inside the directory, and it will generate the skins for it. So this is and texture for it, obviously. So it will generate button 01.png texture and so on. This will generate an atlas. It's similar, as I said last week, about the G asset manager that can generate the textures after it loads it. So if it encounters these two files and you call the generate textures, it will assume that the font underscore UI.png is with the .fnt file, and it will generate a font texture atlas for it. And the PNG, if there is just the PNG without the XML or FNT file, it will generate the standalone texture. And it will ignore these two. These are there just for the minimal components, because as you can see, I'm using minimal components, which is great ActionScript framework for using components inside the native display list. This is not rendered on GPU, this is natively inside Flash, and I didn't use Flex because I kind of hate Flex. It's overly complicated for stuff we want to do. So these are all the assets, and it will generate textures for them, and since it's a UI editor, it will assume we want skins for them, so it will generate texture skin, texture skin, texture skin, and font skin for this one, and texture skin for the untitled. These are used for testing 9 slicing. I will show you. So back to the editor, and now we have these elements without any skin. So we will say this is a font, this is a button 01 skin, and we will tell this is a 2 and this is 3. As you can see, all of them are on default values, so they are in the middle because default value is anchor 0.5, 0.5, 0.5, 0.5, so both there are vertically and horizontally in the middle. So let's move them. Let's move the first one somewhere, let's move the second one and the third one, and we can also, so let's say, even though we have just 3 buttons, we will use the fourth one. So as I move this, it needs to calculate a lot of things because we just moved it, so it will recalculate the anchor X and check the anchor left, all the stuff. I will show you inside the prototype. Let's just check it as I was talking about the relative positioning. So this is the our main container, which has set the anchor to anchor left 0, anchor right 1, anchor top 0, anchor bottom 1. So it will stretch to the whole size of the root, which is specified on its specific. Now we have it specified on the whole stage. Oh, let me pause here and explain to you what the green stuff is. It is actually a feature that was available inside the 1.0, late 1.0, probably some of the latest builds of the previous Genome2D version, and that's when I introduced these virtual screens. It's a special component called G camera controller, and what this does, you can specify a viewport that it has to emulate. And with this component, you just specify, let's say I want to, because if I design games on mobile, most of the time I choose a resolution or a device and I stick with the resolution, and now says to myself that all the other hardware stuff will somewhat scale or move or align to the main resolution I am designing my game in. So let's say I want to target iPad Retina stuff, so we have a 2048 resolution by 1536 pixels, and if I don't have any kind of tooling for that or any kind of component for that, I need to somehow scale the root node, or I use my own camera, which is preferable and it's way faster than scaling, and I need to manage the viewport stuff and so on. So this is what the G camera controller, if you set a viewport, does. So here what I did for this editor, I choose my resolution, my virtual resolution, as the Retina resolution. So this emulates 2048 by 1536 pixels. As you can see, this is not 2000 pixels, so it will scale. I specified it to scale down and maintain the aspect ratio, and I specified, which you can, that it should always align in the middle, horizontally and vertically as well. So this is actually the virtual screen 00, and this is the actual screen 00, which you can get from the G camera controller viewport. It has these properties. I can show you actually. Let's say when we have our viewport, it's inside the scene editor. This is the viewport. So we can get a viewport instance and ask what's the screen left, right and top, and what's the actual view right, left and top. so you can position stuff accordingly. If you position it to the screen 0 0 is here. If you position to the view 0 0, it's here, or the other other way around. I'm not sure yet because I didn't work with it. I just use real coordinates. I don't need to position it outside of the screen. Didn't need it yet, but you can. So it's easily, you know the absolute screen coordinates and the virtual screen coordinates at all times. You don't need to calculate them, which can get kind of complicated. So this green stuff here tells us what's outside of our virtual screen. So if we are designing a game for this screen and we are not taking it into account, we want to stay always here. Of course, if we have some kind of game or tile map or stuff like that, it can go right, left, or the stuff that doesn't matter, which we didn't position, we just tell it to be in the middle and it's large, so it can show outside of the screen. Why not? We want to utilize the estate of the screen as much as we can. But if we are designing for this virtual screen, all our elements will just be inside the virtual screen. Because if we put this button somewhere here and we run this on iPad 3, let's say, with the Retina resolution, it will not be visible, obviously. So that's why the UI editor shows us we are inside some specified virtual screen. And as you can see, now you see two things. The viewport inside the G camera controller works as expected. Now we are in the portrait mode. It scales as it should, and it's now aligned centrally and vertical. And the second thing, the UIs scale with it. Because that's the camera stuff working on. The camera tells us this should be zoomed or unzoomed by some fraction. This is not the UI framework working on. This is the camera. So this will work for our game as well. If we have some kind of platform stuff going on, not just the UI, it will scale for us. And since it's the camera, it's all GPU calculated. There is no CPU invalidation going on, no hierarchical. If let's say if you had some kind of scene or hierarchy zooming, and you scaled the root, and you had like 1,000 children there, it would need to invalidate all the 1,000 children there because the roots scaled, so all the children scale. This is not going on. This is just the projection metrics. Utilize the camera and it will scale on the GPU. So now let's show some kind of UI stuff going on. So we have this root element as set. It's on our whole virtual screen, and let's scale it somewhere. Oh, now you can see that since these buttons are told to be in the middle, and now if we obviously offsetted it by some kind of absolute positioning when we moved it, but the anchor is still in the middle. So now this button has anchor here in the middle of this. I can actually show you. This is the anchor of it, and it has an absolute positioning. I can tell minus, let's say, 200 and minus 10. So if we scale the parent, the anchor moves with the parent, obviously, and therefore the UI moves. The button. This is the first scenario, and I showed you last week where the anchor for this are the same vertically. Okay, we can move them, for example, here. Now all of these guys will be absolutely positioned from there. Oh, this guy, not all of these guys, because we moved the anchor for this guy. So these are in the middle. If we check the anchor for those. They are the same, but this has the anchor here. So this guy is absolutely not absolutely, because we didn't move the anchor to the. Now it's absolutely positioned because it has a relative 0 left, 0 right, 0 top, 0 bottom, and it's all absolute position. So now if we scale this, it's positioned absolutely. If we scale it the other way, it will move, obviously. So now it's absolute position. You can as well move it somewhere else. You can have one absolute, one relative. So let's say so now it's relatively to the middle of this guy. Let's move it here. Relatively horizontally, absolutely vertically. So if we resize this, as you can see, it doesn't move vertically, just horizontally. Very similar to the Unity stuff, if you are familiar with the 4.6 Unity framework. And the editing is very similar as well, because I got inspired there. They actually published their UI source code open source. I didn't check it. I didn't have time for it, and I didn't really need it. But for all of you that are interested in it, you can check it out. So the other scenario I showed you last week is, what if I decide to do something like this? So there is the anchors vertical and horizontal are not the same. So left is not the same as right, and top is not the same as bottom. Now what this does, it's fixed absolutely to the corners. So this anchor is fixed absolutely by some absolute value here. This is by absolute value here, this by absolute value here, and this here. So now if we scale our parent, as you can see, it scales. So it's absolutely you can also let's say do this just horizontally. So now if I scale this, it just horizontally positions, but it will scale itself. So where it's vertically is positioned, but it will scale horizontally. Let's just add some kind of text here. So let's have text. Hello. Let's just make this a child of the element. Hello. It will not scale since this has its own anchors, and it's not told to scale. It's just anchored in the middle of this button. It will just position it itself. So if we scale the parent, as you can see, it just positions itself in the middle of the button. Doesn't matter if the button itself scales. So our labels will not scale. Another thing I wanted to show you, and I kind of started it last week, is that Genome2D UI system supports slicing. Not just 3 slicing, 9 slicing, it actually supports any slicing, or any grid slicing to be precise. Let me show you what that means. So let's choose some better representation for this. Now we have this, I will show you, we have this texture inside. It has just one slice, and that's the whole texture. so it will not slice in any way. And let's say we want to slice it by standardly, so which is standard slicing by the same by the grid basically. So let's go to the asset editor, and this our slice tool will tell us where the slice is, and let's set the slice in the middle. Now if we go back, voila, as you can see, this stayed the same and the middle is sliced. What this does, it tells the engine, the framework, which part should slice. So there is on the GUI texture skin, there is just 4 parameters which specify a single rectangle. So there is a slice left, slice top, slice right, and slice bottom. And that specifies this rectangle, and it specifies the rectangle that should scale. So anything that is top left, bottom left, bottom right, or top right, it will not scale. It will there will be just the middle, the specified rectangle, which will scale in both, so horizontally and vertically. Anything that is to the left and to the right of the specified rectangle will scale vertically, and anything that is on the top, so this rectangle, and on bottom will scale horizontally. And this way we can specify pretty much any slicing we want. This will now tells us, and I will show you. Voila. What this basically did is we changed it to be the three slicing. Hey, so the whole thing. So because everything on the left and the right is from the 0 to the texture height is inside the specified stuff. The whole thing will scale vertically, but just this middle stuff will scale horizontally. So 3 slicing. What we can also do is let's say 2 slicing. We specify this like this. This part on the left will not scale vertically, it will scale horizontally, obviously. Not horizontally, it will scale vertically. And this whole slice on the right, since it's the part specified, will scale in both ways. Voila. So if we have some kind of button with the icon on the left and just the stuff on the right that we want to scale, it's doable. Also, we can specify like this, which is 4 slicing. No problem at all. As you can see, the top part will not scale vertically. This will not scale horizontally. We can also specify the other way around, so no problem. Like this. So this way, without having 4 components like for this slicing, and this slicing, we have just one texture skin, and you can specify the rectangle which specifies the slicing that is going on. It's pretty convenient, it's super easy to set up, and it's optimized. So if you don't specify any slicing, it's pretty much it's as fast as if you had an extra component that would just do non-sliced rendering. Now I want to show you the second part of the UI. I'm not so sure because we are already on the 30 minutes, but let's say I want to show you that prototyping, because a lot of people were asking me if it's feasible to do some kind of text editing of the UI, and because a lot of people are familiar with the HTML and stuff like that, they have as their graphics people either use some kind of UI like this, which is pretty convenient, or some kind of markup language to specify the UI, and it's easily editable. So I decided, as pretty much anything in Genome2D, that the UI will be prototypable. Prototyping is going minor refactoring as well, but this has no impact on the UI because the UI is already using the refactored prototype stuff. So let's show you a new editor here, and that's the XML editor. This, ladies and gentlemen, is actually the scene before us. So the element, which is the main, and all the children with the specified skins and stuff going on. As you can see, the root element doesn't have any skin. if you want the root element to have a skin, no problem. For example, you have a container that has a background, no problem at all. It just doesn't need to have a skin. And as you can see, I'm now pretty much screwed because you can't delete the skin here inside the editor. So now I can't remove the skin for the container. We can however go to the XML editor, and okay, now it didn't invalidate. Now I forced it to invalidate. We can go to the XML editor and remove the skin. Hey, now it invalidated based on the XML, and as you can see, it deleted the whole screen and recreated it from the scratch. So as you can see, it recreated it as it should. I know this is not exactly readable. You can use external editors for XML or just modify this in any way. Another thing is that it doesn't know if the value, you could add this functionality, but it doesn't know if the value is the default value. So it will tell it if we removed, for example, this, or okay, anchor X and anchor Y from here and invalidate it, it would look the same, because the anchor X and anchor Y had a value of 0, which is the default value, and you don't need to specify it inside the prototype if you want the parameter to have a default value. But the editor doesn't know that that's the default value, so it will tell you all the values. Obviously, you could do some kind of matching that would ignore the values that are the default values if you know them. The prototyping system has some kind of default values, but it doesn't know that those are the default values. We could, or I could, obviously, add that to the prototyping, but it would be a lot more verbose. But it's doable inside Hexi, because Hexi can have tags or metadata with values. So I can specify a metadata which will also tell that it has some kind of default value. I hope you are not confused too much, but anyway, what I want to say is that this XML can be a bit more or a bit less verbose like it is, because, for example, even these floating points, you don't need them to such an extent, to such precision. And if I ignore all the default values, it would be very small XML. So for example, let's say I want, okay, I will have just the top element there. Let's remove all these other elements. Now I'm going to, so it has just one element. Is the main. I can, as I said, I can remove the default values. I can round these other values, and the XML is a lot less verbose, and your graphics guys, or the guys that will design the UI, can work with it pretty much as with for example the CSS. Okay, I'm not going to do that because we are running out of time, but as you can see, it's pretty self-explanatory. It's just the hierarchical XML structure with all the properties which can be set that I already told you about. So the prototyping engine for the UI knows that it can set all the properties according to their values. So if you want to specify a skin here, you need to specify an ID. Obviously you can't specify a reference or a pointer to in a memory to some kind of skin inside the prototype, which is a textual stuff. That's actually why inside Genome2D almost everything can have an ID. A lot of people ask me why there is a texture IDs and why there is a skin IDs and stuff like that. This is why, because once you have an ID, you can very easily serialize it into a textual form. So if you have some kind of skin library and you do your asset management, like you load the assets and then you create textures and create skins with their specified ID, you can then reference all these skins in a textual form. So this is why we have some kind of such a complicated ID, because this uses it actually goes by files on the hard drive, load them by their URL, then creates the texture with the ID of the URL, and then it creates a texture skin with the ID of URL. So that's why we have such a verbose ID. You can have any IDs you want. You can specify your own files that will load, for example, assets, and then ID them from the prototypes. We can also save it, obviously, and if we load it again, let's compile it again, it will load our prototype. Super easy, super fun for me. That's all for today about the UI. I will talk about UI in the future devcast as well, so don't worry. I will talk probably about as you could see, the font skin and how it works, because the element doesn't render anything. It just tells that it has a skin, and the skin is the renderer. So there will be a font skin that renders texts. Now, as I said, I'm going to talk about the refactoring. We are already on the 40 minutes mark, so it's about time. Some of you which follow me on Twitter maybe catch that I am working on a series of optimizations inside Genome2D that will bring the node rendering up to speed with the direct context draw. So actually, if I do all the optimizations that I have in my head, it will be even faster than the context render drawing inside ActionScript used the Swig. Because if you do, let's say, if you do 1,000 context draw calls inside an ActionScript to a Swig file, it can't inline those calls. So there will be actually 1,000 function calls. But if I do all my optimizations on the Gnode, they will be obviously inlined inside the Swig file. So they will render with the inlined speed, so they will actually be faster than the context calls inside ActionScript. Obviously, if you work with Hexy, so you will be inlined directly to the context draw. So in the Hexy, the context draw calls will be faster than the node, because it will be the calls without the additional overhead. These are my estimates though, so we will see about the speed. There are actually 3 parts about this refactoring that I'm going to do. The major refactoring is the first part I'm doing now. The other 2 parts are not that much about refactoring, but about doing some kind of new stuff. Especially the third part that came to me when I was doing a research on image compression, and it kind of gave me an idea how I can work. But it's a very complicated. It's directly on a shader. I would say it's some kind of hybrid shading combination with a buffer and vertex shader and some kind of magic. We will see. That's a really complicated idea I have in my mind. That will be the last idea and it will take the most time. The second part that I will do later is about the internal representation of the hierarchy and how it affects the function calls and non-inline overhead. That's the part I will be doing after I'm done with the refactoring, and this second and third part should and will probably have 0 to very small effect on the actual APIs you guys see. So there will be no changes like, okay, I have now my project in 1.1 and I need to change tons of calls. The second and third part of optimizations should have a very minimal impact on the API. The first part I'm doing now, and I already said on the Twitter, is about Genome refactoring, and it has some really big, or not really big, because you can change it with a simple replace script, but it has a impact on the API and how we worked with nodes so far. So the first major stuff, and this stuff was a long time coming. I had tons of requests to change this. It has actually 0 impact on the performance, 0 or very minimal, around like 3% on a bad day, and that's to remove the transform. So there is no longer a transform component. The transform component was, when I started on the Genome2D component model, the transform component was added first I saw it in other component-based frameworks, and it was a good idea to have a transform as a component, because it was in a group with the other components. It had a similar functionality, and the idea was that maybe in later versions, or maybe you guys can create your own transform components, so the node could have a different transform component that would work somehow differently anyway. But for in the years that you guys and me are using the Genome2D, there was not a single scenario where there was a different transform component needed. So I decided to merge the code. Now all the transform stuff is inside the node. So node has all the X, Y, set position, set scale, alpha, visibility, pretty much everything that was inside the transform, so get transform matrix, all the stuff is now directly on the node. It's not a component. So now you can't have obviously the different transport component for a node, which no one really used anyway, and you have a lot less calls, because node transform, though there is no transform anymore, node transform was a getter call and X was a getter call. Now, since if you are just accessing it through X, there is a node. X is just a single getter call, so it's faster. So this is really an impact on a performance, especially inside ActionScript, because inside Hexi this is all inlined, all the getters are inlined. So in ActionScript it will have a really impact on the performance, and it's kind of more readable inside the Genome2D code, and a lot of people wanted it, pretty much wanted it. A lot of people wanted just native feel of Node, X, Y, and stuff like that. So there was not a single person that told me when I asked that we really need the transform. Outside of the obvious reasons, like we are working with the transforms, so we are pretty familiar with it. But I have a huge project on Genome2D, and I moved 2 of my projects to Genome2D 1.1, and I did it with a simple replace, like this: transform dot to empty string. It will work because everything that was in this domain moved to this domain. The other, and this is the optimization part of the refactoring of the first. This is still the first part, and I'm not going to talk about the second and third part that wasn't even started yet. The other major part of the first part of the refactoring for the optimization is that I kind of made the G-sprite and G-movie clip obsolete. They are still there. They are still there. You can use them. You can node, for example, vars sprite, G-sprite, and you can create G-sprite component still, and it will work. For now, there will be this very small window when I move all the both versions. But what I did is I moved this functionality into the node itself. Yeah, you may be saying now that node is heavy. Yeah, it's heavy. It has around 2,000 lines already. Which is not many, but for a single class, 2,000 lines, it's kind of heavy. It should be more modular. And I will remove some stuff from that, but it will not affect the API. So what I did was move this G-sprite and G-movie clip functionality to the node. So node now has texture. Okay, let's create the node first. Node now has texture and texture ID properties, which was the properties of G-sprite. So if you specify a texture or a texture ID for the node, it will render as if there was a G-sprite. It will be the same. Why we are doing this, you may ask. But that's the optimization part, because if we had this inside the G-sprite, inside the component model, this was for first it was a function call. So the node detected that there was some kind of component that implemented the renderable interface, and it made a function call. And secondly, it couldn't be inlined because the iRenderable could be anything. So you can't inline stuff that can be implemented differently or overridden, obviously, because it didn't know what to inline. So for now this rendering of the texture inside the node is inlined because there is no call to some kind of renderable interface. And this actually, but for the first test, this is not official, guys, so don't cite me anywhere. This bumped the performance of Genome2D for the node rendering around 80%. Just this, because if you have a lot of small sprites and rendering, so you see the CPU bottleneck for the node rendering. If you have huge sprites, this has zero impact on performance, because you are GPU bottleneck, then, and obviously the CPU doesn't need this optimization because it's not bottlenecked. If you have like 1,000 by 1,000 textures and 1,000 of them, it will just crash you because of the fill rate of the GPU, not because there is some kind of renderable interface call. And secondly, there is this animation stuff that will, it's not transparent yet inside the version I'm just testing here, but there will be an animation which is a special property for the node that will specify how this node texture change over time or over rendering. It will be very similar how Gmovie Club works. It's just inside its render. It changes the texture it's going to render by some rules, depending on its frame rate, on its specified texture frames, on its specified vector. So if it's playing forward or playing backward. So there will be this animation controller that will control the node texture property, very similar to the movie clip. So now you can have a lot more nodes rendered at the speed of pretty much the context draw call. So now this is everything I wanted to tell you about the refactoring for the 1.1 version, and keep looking for the next devcast. And I hope this first part of the refactoring, which is still going on, I'm just showcasing it here, will be done by the next devcast, and I will be on my way on the second part of the refactoring, which will be probably the biggest performance increase. It will increase the rendering of the nodes inside the action script used this week beyond the direct draw call. So I'm really interested in my Nexus benchmarks, because they will be probably even higher than last year, because the benchmarks I did on my Nexus 7 last year, when I compared Starling and Unity and stuff, they were the ActionScript benchmarks, and they used the SWIG file. They were not the Hexi benchmarks. Hexi benchmarks would blow that thing away, because you could pretty much inline. If you scout and you use an advanced telemetry and scout the Hexi framework inside Hexi, so Hexi version of Genome, and you, for example, have some 1,000 sprites rendered using the direct draw calls to the context, and you scout it inside the Adobe Scout, all you see is just the call on the GPU. That's what tells you that everything that can and is inline. You don't see any functions calls, you don't see any construction going on, any garbage collection. You see just thousands of these GPU calls. So there is nothing to optimize further. And so this will bring the benchmarks into even higher numbers, the second part. And the third part, which is the shader part, and will be probably very huge. It will be very dependent on the scene structure. I got this idea from the image compression and how some kind of lossless prediction algorithms work. So I just got this idea how to optimize rendering for a specific scene structures. Not too specific, so it's used for like 1% of the scenarios. It's just optimize based on the scene hierarchy, and some scene hierarchies can be optimized better, some can be optimized less, but all of them can be optimized, except if you have like artificial scenes with like everything is moving and everything is changing. You know the case. Like I have, for example, 100 sprites, and each has a different texture on a GPU and stuff like that. So I'm very exciting about the stuff I'm working on Genome2D, and I hope you guys are too. So let me know what you think about the refactoring and about the changes to the API. If you miss the transform and miss the gsprite, of course you can now use the gsprite. Still, you use the gsprite, and the irrenderable components will stay, because specific components that you want to render stuff are still viable. This just applies to gsprite and gmovie, because that's the base use case. There are really a lot of games where you have like 10,000 or thousands of sprites going on, and it was a waste of function call, waste of performance to have this simple scenario inside the node. but there are not use case where you have like thousands of tile maps, obviously, thousands of tile maps inside the scene hierarchy. So tile map or a particle system or stuff like that is still a renderable component on a node. So, and you can still design your own renderable components in mind, where the function call doesn't matter, because even if you had like 100 of particle systems, 100 of function calls is still pretty much nothing compared to the actual stuff that's going on inside the 100 of particle systems, obviously. But 1,000 function calls compared to what's going on inside the 1,000 of sprite renderers is a lot. The function call was actually a lot of the time that actual rendering of the sprite takes. And of course, guys, let me know about the UI. What do you think about it? What do you think about the prototyping? And what can I do about that to bring it to the satisfaction of most people? Thank you, and looking forward to feedback. See ya, guys.